tag, but I happen to know there's some blank name tags here.
But you must write your name.
You must write your name. So the next speaker is Claude Lebrun from Stony Brook, and he's going to talk on an introduction to canonical metrics.
Well, before I begin,
so I hope that I'm easier to hear now. In particular, there are many experts in the subject in the audience, and I want to assure everyone that this lecture is not for them. I hope that they'll find it entertaining, but they're certainly not going to learn anything. So I've been asked to talk about canonical metrics, which is a dangerously broad term. But really, there is a general problem called the canonical metric problem that was, for example, articulated around 1960 by René Thom, who said, does a manifold have a best metric on it? It's an extremely vague problem when you state it like that. But so this is an area of mathematics where you should understand that really it's driven by a certain paradigm, by a certain model. And so the classical result that motivates this is the uniformization theorem for Riemann surfaces. Which seems to date from 1907. It seems to be due to Poincaré and Koebe. So if you're given a Riemann surface, so the underlying smooth manifold might look something like this. Given a two-manifold, a real two-manifold, and a complex structure on it, so I'll clarify this notation in a moment, then there exists a unique Riemannian metric G on sigma of unit volume and constant Gauss curvature, which is compatible with the almost complex structure. Now here, in general, an almost complex structure on a manifold M is an endomorphism of the tangent bundle. So it's a tensor field which maps the tangent bundle to itself with square minus the identity. And that allows you to think of the tangent bundle as a complex vector bundle. Now, one special thing that happens in the two-dimensional case is that an almost complex structure is integrable. In higher dimensions, that's not true. So such a structure is called a complex structure is an almost complex structure which is everywhere locally isomorphic to the standard one on R2n equals, maybe I'll call this R2m equals Cm. We're here. So such a thing can only exist if the manifold has even real dimension. And so in two dimensions, an almost complex structure is actually always a complex structure. So in this case, there is no obstruction, but in higher dimensions, there is. So most almost complex structures are not complex structures in higher dimensions. There's an obstruction called the Nienhuis tensor. So if m is bigger than 1, most almost complex structures are not complex structures. Okay, so this theorem is, in particular, all you have to do is to choose an almost complex structure on a surface. Is you could choose some background metric and an orientation and define J to be rotation by 90 degrees, and then in fact the metric that you're promised would be a conformal rescaling of the given metric. It would be the original metric times a function. But the situation in higher dimensions is quite different. So the way that this is proved classically really depends upon the fact that one has a complete description of simply connected spaces with constant Gauss curvature. They are up to scaling. So the key point, which was discovered by Poincaré, is that the universal cover is the two-dimensional disk R2 or the standard two-sphere. And in these cases, when let's say C. So in the cases when it's not simply connected, then it turns out that there's the fundamental group actually acts on the universal cover in a way that preserves a standard metric. So the hard part of this theorem was, which was considered hard in 1907, was to show that a simply connected Riemann surface had to be one of these three candidates. Now that sort of simmered on the back burners of mathematics for a long time. There has been a huge amount of activity in the theory of Riemann surfaces since then, which exploited this kind of uniformization. The key thing is that from the point of view of algebraic geometry, this is a sort of strange theorem, because the way that Riemann surfaces arise in algebraic geometry is as projective algebraic curves. They have natural metrics on them, if you like. If you have something embedded in projective space, you can restrict the metric from projective space and say, well, I have a natural metric. But as you take different projective embeddings of the same curve, you'll get different metrics. And that does not give the curve some kind of natural metric that's just determined by its algebraic geometry. course, this proof is particularly alien to algebraic geometry. Algebraic geometers do not, people that like to work over fields other than C really do not like things like the universal cover, because this object is not an algebraic object. It's not, the kind of algebra that comes in is not the same kind of algebra. So the key event for my talk today is a pair of papers by Calabi in 1954. So this is a very good example of the fact that mathematics does not have to be completely correct to be important mathematics. So one of these papers was actually the proofs he sketched are definitely completely wrong, and the thing he thought he could prove at that time is slightly wrong. But in both cases, these papers, his vision was actually incredibly profound. So the idea, so let's just say he proposed, he thought he could actually prove a lot of these things, and it turned out on closer inspection that there was a lot more to be said. He proposed that a generalization of this uniformization to higher dimensions. So specifically for higher dimensional compact complex manifolds of Kähler type. Now, the sense in which this is what Calabi's program is not a uniformization is really a very misleading word here. When one says that a Riemann surface is uniformized, you're actually saying that, well, look, its universal cover is a standard model, and the fundamental group acts on that standard model, preserving a fixed preferred Riemannian metric. The important thing is to look at that there is a curvature equation here. And what Calabi proposed doing was to forget about the structure of the universal cover. He wants to do something that will work in particular on simply connected manifolds, and there are lots and lots of different ones in higher complex dimension. But he wants to focus on generalizations of this condition. So so one of these papers, which is the famous one, was the study. It provided a picture of Ricci flat Kähler manifolds. And so that one appeared in a volume in it was a Festschrift for Lefschetz. There was another paper that's not well known. It's in the ICM, which was held in Amsterdam that year. He had a one-page paper, which is more an extended abstract than a paper, where he looked at a scalar curvature of Kähler manifolds. Now, both the Ricci curvature and the scalar curvature are ideas from Riemannian geometry. They make sense for for general Riemannian manifolds. And I'd like to now take just a few minutes to talk about what those concepts mean for a Riemannian manifold. So Calabi's program is specifically about complex manifolds. There is this more general question asked by Tom, which was, if I give you a smooth compact manifold, does it have a sort of a best metric? Is there some way of giving a general smooth compact manifold a preferred geometric structure? By the way, if you look at this, so this is the paradigm, the prototype of the theorem. And if you know anything about the moduli theory of complex curves, or the Teichmüller theory of Riemann surfaces, you know that the complex structure is not unique for a curve for a surface of higher genus, or for a complex curve of higher genus. There is a moduli space of different complex structures, and correspondingly, so here the metric is actually associated with a particular complex structure. So if you're thinking about this as a way of giving a preferred geometric structure to the underlying smooth manifold, it's not unique, but rather there's a family of constant curvature metrics. So let me just say a few words about the curvature of Riemannian manifolds before we focus on the Kähler case. So the Riemannian story can be explained in the following way. So remember, so suppose that we have some n-dimensional Riemannian manifold. And this, right now, I'm not assuming that it has anything to do with complex geometry. Then there's an extremely important notion that's associated with the metric g. So what is g? It's an object which allows you to measure the length of tangent vectors. So g determines geodesics, which are locally the shortest paths in the manifold. And you can use that to define, I'll assume for simplicity that this M is compact. Otherwise, you have to take the picture I'm going to draw with a little grain of salt. So there is a nice map. If you're given a point on the manifold P, choose some base point, then there is a nice map from the tangent space to the manifold called the exponential map. And that exponential map does the following thing. If you're given a vector, then you can follow a geodesic in the direction of that vector for a distance equal to the length of the tangent vector. So there's a so-called exponential map from the tangent space at P to M, which is a diffeomorphism of a neighborhood of the origin to a neighborhood of P. So if you choose an orthonormal basis for the tangent space, this actually gives you a canonical way of assembling coordinates on the manifold. Just give it a Riemannian metric, a choice of point, and some orthonormal basis for the tangent space. Choose an orthonormal basis. So the remarkable thing is that one gets different. So you could ask in these coordinates, the metric has components which, to lowest order, look like the Euclidean metric. If you pull back the metric to the tangent space via this map, if you were actually in Euclidean space, the components of the metric would just be the components of the flat metric. And then there's a correction term at the quadratic level. And while this is not the fanciest way of cooking up the Riemann curvature tensor, the set of coefficients that you get here is just the curvature tensor. All right. So if you look at the volume form, which I'll crudely write as just d mu, well, it looks like the Euclidean answer and then what's the volume form of this? It's going to be, it corresponds to taking the square root of the determinant of the matrix coefficient. So you would get 1 minus a sixth r jk xj xk, and then plus terms that are of order x cubed. And this thing is the Ricci tensor. So the Ricci tensor is this natural object that is associated with the metric. Like the metric, it corresponds to a symmetric. It's a quadratic form on the tangent space. And so here I've of course expressed it in terms of some coordinate system, but the point is you can think of this as like the metric. It's something which gives you a kind of inner product between vectors. And in particular, if you take a direction in which the Ricci curvature, so given a vector, given a unit vector, you can associate to it the expression the Ricci curvature of the vector and itself, expressed here as the sum of Rijk vi vk. When that's positive, that says that the volume of a small cone in the manifold is less than it would be in Euclidean space. You also see there are components here. You can simplify this in dimension 2 that would turn out that there would only be essentially there's a single number called the Gauss curvature which determines the entire curvature tensor in dimension 2. And so what Gauss had discovered was a very special case of this thing later on cooked up by Riemann. So the Gauss curvature, or more generally the sectional curvatures, control how distances between geodesics behave, whereas the Ricci curvature controls how volumes of families of geodesics behave. Okay, so this, so if you like, the Ricci curvature measures the degree to which the exponential map distorts volumes. Now, finally, there is something called the scalar curvature. So here we've introduced something called the Ricci tensor. There's the curvature tensor, and then there's the scalar curvature. Which I should say that the way that historically the Ricci curvature is defined as the trace of the curvature tensor, and the scalar curvature was defined, historically by saying what's the trace of the Ricci tensor, but it has the following very simple, nice geometrical meaning. So if you're in your Riemannian manifold, what you can do is, given a point P, you can look at points that are within distance epsilon of that point P and ask, what's the volume of this ball? You could then divide it by the answer that you would have gotten in Euclidean space. So that would be epsilon to the n times the volume of the unit ball in Euclidean space. And then there's a similar expansion for this. So the volume of this ball would look like the ratio is 1, and then there's the error term occurs at the order of the radius squared, and it would end up being the scalar curvature at the point P divided by a nuisance factor of 6 over n plus 2, and then their higher order terms. So the scalar curvature is sort of the simplest invariant that you could imagine to determine how different your manifold is from flat space. When you measure the volume of a small ball, you could ask, is that the same as it would be in Euclidean space? If the scalar curvature is positive, the volume of a small ball is smaller than it would be in Euclidean space. And so when the scalar curvature is negative, the volume of a small ball is bigger than it would be in Euclidean space. All right, so there's a very special class of manifolds of interest. I mean, we could look at interesting conditions on the curvature that are built by looking at conditions on the Ricci curvature or the scalar curvature. We could also, of course, try to ask that the Ricci tensor, the full curvature tensor looks like that of a sphere. So something of constant sectional curvature could also be thought of as that's an interesting equation. But if you look at the number of components here, this has in high dimensions many more components than the curvature tensor. The number of components of the metric tensor. So the number of components of the metric tensor grows quadratically in the dimension. The number of components here grows quartically. And so you're looking at too many conditions if you try to say, find a metric for which its curvature tensor looks like the standard thing. You don't stand a chance if you think of that as a differential equation. Whereas if you tried to say, well, maybe I can require that this quantity is equal to a constant for independent of the choice of a unit vector. That's so when you try to generalize this notion of constant Gauss curvature, the Gauss curvature is a number that determines the entire curvature tensor of a two manifold. If you're trying to think of how would I generalize that to higher dimensions, the obvious candidate might be the scalar curvature, because the scalar curvature, like the Gauss curvature, is just a single number. But then, if you're thinking on the level of an equation, it's also very interesting to look at the Ricci tensor. So, one interesting equation to consider is the condition of having constant Ricci curvature. In other words, you could ask that the Ricci tensor applied to a vector in itself is equal to a constant lambda for all unit vectors. And this is equivalent to asking that the Ricci tensor is equal to lambda times the metric tensor. Right, so if you feed two copies of a unit vector here, you get 1. And so it's pretty easy to see that these are in fact the same equation. So this is called the condition is being Einstein. So this equation, in the context not of Riemannian geometry but of Lorentz metrics, was first discussed by Einstein, and he later on repented of the idea that this constant lambda might be non-zero. So he was looking for an equation of what the gravitational field. The metric is denoted by G in Riemannian geometry for a historical reason we tend to forget about. It was the gravitational field for Einstein. G stands for gravitation. This equation Einstein later called the greatest mistake of his life, and that's why we punish him by calling this the Einstein condition. But of course, you could also instead just ask about constant scalar curvature. So here I should say that this lambda is a constant. And this is called the Einstein constant, again, as punishment for Einstein. In physics, they would call that the cosmological constant. Okay, so if you're just in the Riemannian context, to finish the story, you could begin by saying, well, does every manifold have metrics of constant scalar curvature on it? It turns out that the answer is yes, and there's a generalization of the uniformization theorem for Riemann surfaces. This is a solution for the Amabi problem. So every compact MG can be rescaled so that G hat equals, let's say, G times F, where F is some positive function, has scalar curvature constant. This is a major theorem in Riemannian geometry. It's called the solution to the Amabi problem. However, this doesn't geometrize an arbitrary manifold very well. The reason is that in higher dimensions, in dimension 2, any Riemannian metric is conformally flat. It looks like the flat metric times a function. In higher dimensions, that's not true. In dimension 3, it's already wildly false. So the problem is that if you're looking at Riemannian metrics on a smooth manifold with constant scalar curvature, they always exist, but there are too many of them. There's an infinite dimensional space of essentially different things. So this is a beautiful theorem, it's a useful theorem, but it's not an answer to how do you generalize uniformization to higher dimensions in a way that gives a manifold a canonical structure. So Tom's idea was that you should at least only have a finite dimensional space of geometries on a manifold. If you look at constant scalar curvature Riemannian metrics, that's an infinite dimensional space, even after you mod out by diffeomorphism in higher dimensions. On the other hand, this constant Gauss curvature condition also, for a surface, implies this Einstein condition. And one could instead try to find Einstein metrics on a smooth manifold. So in the general context, not of complex geometry, but just of the problem of one of the main problems in modern Riemannian geometry is which smooth compact manifolds admit Einstein metrics. Now, before the work of Calabi, there were no non-trivial examples of compact Einstein manifolds. So there are these manifolds of constant sectional curvature, like spheres or quotients of hyperbolic space or flat tori, but there were no known examples of Einstein metrics which were not constant sectional curvature metrics. So Calabi did this daring thing in 1954. The first observation he made is that that there's a necessary condition for a complex manifold to admit a Ricci flat metric, which is Kähler. So what he developed in this paper was he gave a conjectural description of all compact Ricci flat Kähler manifolds. And these would be certainly a very important prototype of what we would mean by canonical metrics in complex geometry. So these now are called Calabi-Yau metrics because well, it's a very interesting paper that Calabi wrote. He begins by stating the result as a theorem, and then he says the proof is heuristic, and at the end of the paper he says there may be some gaps here. But you would think that, in those days you would. The problem is that in those days you didn't type your papers in tech, right? You had to get a secretary to type them, and if you realized writing you were probably terrorized by the secretary. You wouldn't want to go back and say, could you please, change this? So it starts off saying theorem, and then by the end he's sort of saying, well, I think that this is actually much harder than I. It doesn't, despite those flaws, this is really a landmark paper, and it's an example that sometimes we have to be a little bit kind when you realize that there's a gap in somebody's work. Sometimes they could nonetheless be doing something very important. So I've just trotted out one of the crucial words, which is Kähler, and I want to put Kähler geometry in the complex context now. And the way to do that is through the notion of holonomy. So if you have again, I'll say I'm looking at a general Riemannian manifold, although I'm actually drawing like something that looks pretty much like the northern hemisphere of the round 2 sphere. Again, choose some base point, and then imagine that you choose some piecewise smooth loop based at this point. So it doesn't have to be. It doesn't have to actually be a smooth loop. The point is that there's a notion of these geodesics on a manifold arise from a certain connection. So there is a connection determined by G by a couple of conditions. It's a torsion-free connection, and it is metric compatible. The key thing that this object allows you to do is there is a notion of carrying a vector along a curve in such a way that it's parallel to itself. So this is the generalization. In Euclidean space, if I give you a vector at a point, you teach your undergraduates all the time that, vectors at any point in Euclidean space, they're all the same. But there's an issue in a Riemannian manifold. If you start with a vector at one point, then you can try to carry it along your curve in such a way that its covariant derivative is 0 along the curve. And the problem is that when you come back to your original point, generally speaking, it's another vector. So parallel transport around a loop will not, in general, be the identity. So one gets a family of maps called the so there's a set of maps linear maps from the tangent space to itself gotten by parallel transport around loops. So the holonomy of a Riemannian manifold is the holonomy group of MP is the set of the linear transformations from the tangent space to itself induced by parallel transport around loops. Now, for a Riemannian manifold, parallel transport preserves the length of vectors and therefore preserves inner products between vectors. This is automatically contained in the orthogonal group of the appropriate dimension. And if you restrict to loops that are null homotopic, you actually get a connected group, and it turns out path-connected subgroups of Lie groups are always Lie groups. So in fact, you get the holonomy group of a manifold is always a Lie group, a subgroup of the orthogonal group in the appropriate dimension. So of course, to identify it with the orthogonal group, you have to choose an orthonormal frame. Strictly speaking, you should say that the holonomy group thought of in this way is only defined up to conjugation. So there's a very special and interesting case. If the holonomy, let's say if n is even and the holonomy is contained in the unitary group, then the metric is said to be Kähler. The thing I'm trying to emphasize is that this is a natural notion that arises in Riemannian geometry. The Kähler condition is not something, I mean, Kähler metrics were discovered in this really weird way. It turns out that Kähler metrics can locally be written in terms of second derivatives of a potential function. Kähler wrote down some metrics of that kind. Then he computed their Ricci curvatures and found, wow, there are these amazing formulas for this stuff. And he published this. No one had any idea what it was for, where it came from. But in fact, it was realized by Chern and by Berger in the late 50s that, in fact, the Kähler condition is just saying that parallel transport is a unitary transformation and not an orthogonal transformation. And what's the difference between the unitary group and the orthogonal group? It's the intersection of the orthogonal group with the general linear group over C. Right? So that's exactly saying that parallel transport is complex linear. When that happens, so if parallel transport around loops is always complex linear, you can then define a natural almost complex structure on the manifold by, you take the almost complex structure the holonomy preserves here and drag it to any other point along any path. And if you choose a different path, it'll be compatible because you find that because parallel transport around loops preserves this J. So the Kähler condition one way of saying it is that it's the holonomy is contained in UM. A second equivalent way of saying it is that there exists an almost complex structure J, which is invariant under parallel transport, and that's the same as saying that its covariant derivative is 0. Now, these are not the definitions of Kähler that you would see in a book like Griffiths and Harris, or actually any book that would typically be given to an algebraic geometer who wanted to learn some transcendental methods. The amazing thing is that, so this, when you take the covariant derivative of J, this splits up schematically into two pieces, the Non-Hausdorff tensor plus the exterior derivative of the associated Kähler form. So the Non-Hausdorff tensor the Non-Hausdorff tensor is the obstruction for J to be a complex structure. Which this is a locally standard. And by the way, this history is arbitrary and cruel. So this was also discovered by other people like Fröhlicher, but it's usually named after Non-Hausdorff. The Kähler form is the 2 form defined by setting omega, which you can feed 2 vectors, is the inner product of Here, let me be specific. Omega of VW is G of JVW. So here, J, without loss of generality, can be chosen so that, so if there is an almost complex structure which is invariant under parallel transport, there always is one which also has the property that it is an orthogonal transformation with respect to G. And with such a thing, if you now look at the tensor that you get by feeding J into one slot of G, this turns out to be a 2-form. When I say it's a 2-form, of course, I'm saying that omega of VW is minus omega of WV. And so now it makes sense to ask for this 2-form to be closed. So the usual way of describing a Kähler manifold in standard textbooks like Griffiths and Harris would be to not talk about this Riemannian story at all, but to instead say you begin but with a complex structure, and then you have this 2-form on the manifold which is invariant under J. That's to say, it's a form of type 1,1. And such that the metric, the inner product that is defined by it in this way is positive definite. And then that's described as a Kähler manifold. So in particular, you may find it confusing at first. Many experts in the field, when giving a lecture, will refer to omega as the metric. It determines the metric. It's not the metric. It's a skew thing. It's not. But of course, as long as you're careful about understanding what's being said, then it doesn't lead to unnecessary confusion. All right. So so given a Kähler manifold Mg, and for clarity, we're fixing a compatible almost complex structure, integrable. It'll automatically be integrable. Then omega has a de Rham class In fact, it's not an arbitrary de Rham class because this form is of type 1,1. And under the Hodge decomposition of the second cohomology, there is a decomposition of the cohomology into types. So here, the H11 is usually defined over C. You take its intersection with real cohomology. And so the point is that there's a cohomology class of omega, and then this is called the Kähler class. One very important and interesting thing you can do is to, fixing the almost complex structure, you could ask what are the different metrics that determine the same cohomology class. And so different choices of Kähler metric with the same Kähler class are related in the following way. As I said, if you know the Kähler form, you can reconstruct the metric. And if you have two closed 1,1 forms in the same cohomology class, then there's a so-called DD bar lemma that they differ by I DD bar F, where here, so D has been written as the sum of the operators that increase the two different terms in the bigrading. So starting with a smooth function f, let's say if we're looking at only smooth metrics, you would take a smooth function on the manifold, and you could now modify the Kähler form in this way. There is a constraint on this F because we want this to still determine a positive definite metric, and that puts some global constraint of pseudoconvexity on this function f. But the main point is that if f has small second derivatives, if it's small in the C2 topology, if it's close to 0 in the C2 topology, then this would always produce a new metric. And in particular, that shows you that the space of Kähler metrics compatible with a given complex structure and Kähler class is, first of all, it's infinite dimensional, but it's essentially determined by one free function. So on Riemann surfaces, one tends to modify the metric by multiplying by a function. In higher dimensions, that won't work, because if you multiply if you're keeping the same j and you multiply the metric by a function, that also multiplies omega by a function. When you take d of a function times omega, you get df wedge omega. That would vanish on the 2 manifold because it's a 3 form. But in higher dimensions, this will turn out to never be 0 unless f is constant. And so you can't proceed by that kind of conformal trick, and instead you have to use you have to proceed by studying these so-called Kähler potentials. So this would you could also play the same game locally by writing a Kähler form simply as IDD bar f in local coordinates. But if you want to work globally, where you're in a non-trivial de Rham class, well, what you do is you modify a given form by adding IDD bar of a function. All right. So what did Calabi do? Well, I mentioned these 2 papers. One is a picture of Ricci flat Kähler metrics. And so the so-called Calabi-Yau theorem, which is stated as a theorem by Calabi, and it is now a theorem now, but the key analytic work is due to Yau. It says that a compact complex manifold of Kähler type. So when I say compact complex manifold, I'm fixing the M and a J, but I haven't fixed a metric yet. Kähler type means that there exist Kähler metrics on it. A compact complex manifold of Kähler type admits Ricci flat Kähler metrics. If and only if the first Chern class vanishes in real cohomology. In other words, the integer first Chern class is a torsion class. And moreover, there is a unique Ricci flat Kähler metric in each Kähler class. Okay, so Calabi actually sets up the problem exactly right. All of the in terms of setting up the equation and the continuity method, it's all in his paper. But on the other, so he knew how to prove that there was a key analytic detail which had to be solved by Yau. There were actually several different ones. So this is called the Calabi-Yau theorem. Yau is, I think, 1977. I think it's 78. But it basically it uses exactly Yau's proof uses the method that Calabi had suggested, but but Calabi did not know how to do the estimates that were necessary to show that the equation has solutions. All right, so I'll say a little bit about that in a minute, but I want to talk about the other paper. So Calabi also stated in his ICM paper, or let's say his ICM abstract, because it's really too short to really qualify as a paper, that any Kähler class on a compact complex manifold contains a Kähler metric of a constant scalar curvature. All right, so if this was true, it would be a perfect generalization of the uniformization theorem to higher dimensions. For a two-dimensional surface, the scalar curvature is twice the Gauss curvature. So the fact that we were able to find, after volume normalization, which corresponds to choosing a Kähler class on the complex curve or Riemann surface, the condition that you have a metric of constant Gauss curvature is the same as having one of constant scalar curvature, and this would be a beautiful natural generalization to higher dimensions. Unfortunately, it's not true. Let's say it's not quite true. So this is an assertion which is wrong in ways that are rather subtle. Certainly, so in this paper, Calabi had suggested a method of proof which is actually correct. It's completely correct. In his little abstract, making this bold assertion, he actually suggests a method of proof, and it's actually wrong. But on the other hand, it's a very suggestive idea, and it's related to ideas that do work. Before I say anything else, what's conceptually wrong here? So with hindsight, there's something that goes on in algebraic geometry which makes it clear that a theorem like this cannot work in general. And let's sharpen this up a little bit. The assertion is that this metric is essentially unique. That part is of the story is very much related to something which is true. It turns out that if you have two constant scalar curvature Kähler metrics in the same Kähler class, they are in fact the same up to automorphisms of the manifold. In particular, they're isometric. So this would be a beautiful way of equipping. You take this thing that came out of the world of, well, maybe it's a projective algebraic manifold. Not every Kähler manifold is projective algebraic, but a lot of them are. Suppose you start off with something that came out of the world of algebraic geometry, and now you want to do Riemannian geometry on it. And what Calabi is suggesting is that there is this natural way of giving it a preferred Riemannian metric. So it does depend on the choice of Kähler class. All right, so you can live with that. You also know that, of course, in general, you can deform complex structures. So, but once you specify the almost complex structure and the Kähler class, the hope was that you would have a natural Riemannian structure. So what's wrong with this picture? like I said, this criticism of the statement is one that comes with half a century of hindsight. So I mean, I don't want, I think of Calabi as a towering figure, and I don't want to sound overly critical. But there is something deeply wrong about this program, and the problem is the following: the space. So Riemannian geometries. So Riemannian manifolds. Say compact Riemannian manifolds modulo isometry. So if you like, these are Riemannian geometries where you consider two metrics really the same as if one is obtained from the other via some diffeomorphism. This is a metric space. And in particular, it is Hausdorff. So if you take the set of compact Riemannian manifolds, if you like, you can fix the dimension, but you don't need to. And then you consider two such things the same if there's an isometry between them. There's a way of measuring the distance between two Riemannian manifolds. So you might get confused. Riemannian metric, that's some kind of some tensor field, and on the other hand, in the theory of metric spaces, one talks about distance functions. But a Riemannian metric does determine a notion of distance. What you do is, given 2 points on a Riemannian manifold, the distance between them is you join them by the Riemannian metric allows you to assign lengths of curves by integrating speed. Right? Take a parameterized curve, integrate its speed, that's its length. Now you take the infimum of lengths of curves, and there's a notion of distance between 2 points. Well, the point is that actually just between compact metric spaces, there's a notion of the Gromov-Hausdorff distance. So the technical details are probably not so important, but the idea is first, if you're given two compact subsets of some metric space, you can talk about what's the distance between those two compact subsets. Namely, you would want to take the smallest number. You take numbers so that the tube around the first, let's say the epsilon tube around the first set contains the second set, and vice versa. And then you take the infimum of all such epsilons. That's the distance between two compact subsets. Now, abstractly, you could say, given two compact spaces, embed them in all possible metric spaces and take the infimum. Now, you don't have to work so hard, because you can just say, given two compact metric spaces, on their disjoint union, I could consider all possible notions of distance on the disjoint union so that it restricts to each one as the original one. Now, because is what you would get if you embedded them in another metric space. But the metric space you're thinking about could just be the disjoint union of the two original things. So now you have a notion of distance on this thing, distance on this thing. Find some notion of distance satisfying the triangle inequality on the disjoint union. Then now say, what's the smallest possible distance between this and that? Okay? So that defines what's called the Gromov-Hausdorff distance between two compact metric spaces. Now, the point is that you can show that if you have two Riemannian manifolds that are two compact Riemannian manifolds that have Gromov-Hausdorff distance 0 between the two, they're actually isometric. So in particular, since that allows you to say that if you sort of think of all Riemannian manifolds of a given dimension has a nice structure. All Riemannian manifolds modulo diffeomorphism in a given dimension has a nice topology. You can talk about how far it is between one Riemannian manifold and another. But the sad fact about complex manifolds, when you're looking at complex structures, is that in general, the space of complex structures on a given complex manifold is not Hausdorff. So here, this now up to automorphism, or modulo diffeomorphism group, which acts on the space of complex structures. This is not Hausdorff. So so this is something you don't see for complex curves. And that's why uniformization for complex curves is a sensible thing. What happens in higher dimensions is that you cannot. I mean, if this worked, there would be some way of given a complex manifold and given a Kähler class, you'd have a canonical choice of Riemannian structure, and then you could measure its distance from any other thing. And that would make the space of complex structures and polarizations, choices of Kähler class, into something Hausdorff. But the sad fact of life is it's not Hausdorff. So I hope that you'll allow me to point out a simple example of why this is the case. For many of you, this is a well-known story, but probably everything I've said so far has been a well-known story to many of you. So just consider the following example. I'll talk about the so-called Hirzebruch surfaces. So first of all, let's just look at the complex manifold P1 times P1. But we can think of that in the following way. It's built, think of this as fibering over P1. And think of this as actually something you build from the trivial C2 bundle by projectivizing, replacing every fiber of that trivial complex vector bundle with a projective space. Now, the issue is the following thing. How do you define CP1? You define it as the space of lines in C2. So you look at the space of lines in C2, and the fiber of this bundle is, of course, C2 at each point. And so you could say, well, let's see. Every point here could be thought of as defining a certain line upstairs. What is that? It's the so-called tautological line bundle. O-1, the standard Chern class -1 line bundle, which parameterizes the different lines of the origin in P1, can be thought of as being a subbundle of the trivial bundle. And so if you then take the corresponding exact sequence by looking at what the quotient is, you can think of the trivial bundle as an extension Now, you could ask, what's the most general vector bundle over P1 that fits into an exact sequence starting here and ending there? An extension of this kind, I mean, locally, you can always find splittings of any exact sequence of vector bundles. And the difference between two local splittings is a map from the quotient to the subbundle. And so such E's are parameterized by H1 on P1 of Hom from O of 1 to O of -1. And that's equal to H1 of P1 O minus 2, which is isomorphic by seriduality to C. What?
What is
So here we have a vector bundle. And the question is, what's the most general vector bundle? So what's the most general fitting into an exact sequence, which starts with O minus 1, the tautological line bundle, and then maps to its dual. Okay? So one such thing is the trivial bundle. So in fact, concretely what's happening here is that the transition functions for such a bundle you could put in upper triangular form, where in this slot you put in the transition functions for O minus 1. Here you put in the transition functions for O1, and then here you put in something which is a function from O1 to O minus 1, and that's the same as a section of O minus 2. Now the point is, of course, this has a natural linear structure, and you might say, well, what are the different things you could get? Well, if you just label the maps, if this map is called alpha and this is called beta, if you multiply this map by t, it's another exact sequence, and that multiplies this by t inverse. So it turns out that, in fact, all of the elements other than the origin represent the trivial. Actually, it's the trivial bundles just with a different map. But there's another thing that there's another obvious thing you could put in there. You could put in the trivial extension, and that's what you get for the origin. Now, that's saying that as you look at all of these, so here's the natural structure on the space of vector bundles that fit in such an exact sequence. These are not the most general picture of a holomorphic vector bundle on P1. It's a little more complicated, but if you're given an exact sequence this way, it's parameterized by a linear space. So if you equip it not just this bundle, but also the maps, you get an element of this cohomology group, and it's a one-to-one correspondence. But what that means is that you construct, just by changing the transition functions, you can find a family of holomorphic vector bundles, which depends holomorphically, in particular smoothly, on another parameter, which at most values is the trivial holomorphic bundle, but at one value suddenly jumps to being something which is completely different. And this is definitely not the trivial bundle, because this is spanned by its global sections. This has no global section, so the global sections of this bundle do not span it. They cannot be isomorphic as holomorphic vector bundles. But now we could play this game. If you look at the projected bundle of O minus 1 plus O plus 1 over P1, then that has to be diffeomorphic to the product bundle. So this, if you just think of P1 times P1, which is diffeomorphic to S2 times S2, is also diffeomorphic to this to this complex manifold. But what you find is that there's a completely smooth family of complex structures, such that when you consider them up to biholomorphism, you have a constant family, and suddenly it jumps. Obviously, the space of complex structures modulo diffeomorphism has to be non-Hausdorff. You've got a constant sequence that has a limit which is not itself. In fact, so this is the so-called second Hirzebruch surface. And when you look at complex structures modulo diffeomorphism on S2 times S2, it's a non-Hausdorff space. It's like one of these things you would see in a first-year topology course, where the product, the standard P1 times P1 is a closed point. It's the only closed point. The open sets are like this. So it's for each. It turns out that if you had instead put P of O minus K, that would also be diffeomorphic to O plus K. That would again be diffeomorphic to S2 times S2. But the space. But what you'll find is that there are families where you can knock down this value of K, where it'll jump in the same way. So the natural topology on this is definitely non-Hausdorff. That means that there could not be a natural way if you take the second Hausdorff if you take the second Hirzebruch surface, and if it was to naturally have a constant scalar curvature Kähler metric on it, you would get a contradiction, because somehow if that was pretty much determined by the complex structure, it would have to jump suddenly when you take a very small deformation of the of the complex structure would have to jump to the product metric on P1 times P1, on S2 times S2. Okay, so in fact, the phenomenon that's I've kind of run out of time here. So I'm sorry. I'll just wrap it up quickly. I'm sorry. So in fact, what's going on here? This, of course, is related to the fact that you can't look at even vectors. If you look at holomorphic vector bundles over a fixed space, that does not have, in general, a nice Hausdorff structure. And you need to put in a so-called stability condition on it before you can start assigning, giving a Hausdorff structure to the space of vector bundles. Now, so the bad thing that happens in this case is that the bundle we're looking at has trivial first Chern class. This for this standard structure, it turns out that the only subbundles like this one have negative Chern class, or zero Chern class. Whereas for something like this direct sum bundle, there is a subbundle that has larger Chern class than the bundle itself, and that violates the condition that's called Mumford stability. So, I was hoping to I tried to say far too much and ended up saying far too little. So the idea is that in order to turn Calabi's assertion into something reasonable, one has to not look at arbitrary complex manifolds with a Kähler class, but there is a stability condition that has to be imposed. And so the thing that you'll be learning about in other people's lectures here are about the correct notion seems to be Donaldson's K-stability. And I was hoping to get around, I didn't even get to the classical Futakian variant, much less the modern one. Anyway, I hope that you've learned something useful, or at least have been entertained. And let's break now for lunch. Oh, it must have been really bad then.
So was this the kind of, I mean, these unstable bundles, was this the kind of thinking that led people to think that the metric condition was related to stability?
Yes. So, for example, some early theorems in this subject were that I proved a theorem about if you look at a P1 bundle over a complex curve, and there's also a condition about the sign of the scalar curvature, the candidate scalar curvature would be negative. Then if there's a negative scalar curvature constant Kähler metric, the corresponding bundle is a stable bundle, polystable actually. So that inspired. So Donaldson had proved a remarkable theorem. In the case of bundles over curves, there's a classical theorem of Narasimhan and Seshadri, which says that a bundle is stable in the Mumford sense if and only if it has a projectively flat connection. And Donaldson found a way of generalizing that to an appropriate Yang-Mills type equation in higher dimensions. So it's not the condition is not that the connection is flat, but you have a unitary connection which satisfies the so-called Hermite-Einstein equations. So all of that fits in neatly with the idea that there has to be some relationship between stability and existence of these metrics. So if you have a CP1 bundle over a curve and it actually arises from a flat structure, if there is a unitary connection on the vector bundle, then you could just cook up. You think of it locally as looking like a product, and you can just take the product metric of P1 times an appropriate constant scalar curvature metric on the base. Right? So there's something else that goes on in an example like this. So the first theorems that would have detected the fact that this is not going to have a constant scalar curvature metric. The first thing that was observed is about the structure of the automorphism group of manifolds. It's first proved for Kähler-Einstein metrics by Matsushima So anyway, people thought for many years that the real problem with Calabi's picture was that you had to restrict to manifolds that didn't carry holomorphic vector fields, that they only had discrete automorphisms. But it's turned out that that's not the case. That there's a sort of shadow world of vector fields on limits of the manifold that you have to take into account. And right, so I hope that you'll learn all about that in other lectures. Definitely not in mine.
Other questions? Thank you very much.
What I find very funny is that usually, and I start seeing all of these terms like Kähler Einstein metric, and many things about Kähler Einstein metrics, I don't realize that they are simply Kähler metrics that are Einstein in the usual Riemannian sense. Or some people might be too embarrassed to ask that question, and they might come and whisper that to you.
That's why you said most